Hello again, everyone. This is Robert Parker from LizardTech, and we'll get started very soon. Just wanted to make another audio announcement to make sure that your audio is working and that you can hear everything. We'll get started a couple minutes after the hour, and just to give everyone a chance to join in that signed up and wanted to be a part of this. The phone lines will be muted for the duration of this presentation. If you do have any questions, please feel free to use the chat feature in WebEx to ask your questions or to make your comments or to otherwise communicate. And we'll get to those as we have time. So once again, just another little audio announcement. Make sure your audio is working, and hopefully you can all hear this. All right, I'll be back with you shortly, and we'll get started soon. Hello, everybody. This is Robert Parker from LizardTech, and we're ready to get started on this presentation. Now, I should point out that the title you saw there may be a little bit misleading. The original title is an in-depth look at MrSID, and that's what we're going to do today. We're going to focus on MrSID compression with a little bit of discussion on other types of compression, but mainly focusing on MrSID and what that brings and what it's all about. It's a very fascinating technology, and we'll be discussing that in depth. For people that might not be familiar with raster imagery, you might want to take a look at the previous presentation on the LizardTech University series, which is all about raster imagery and raster properties and things like that. That'll give you a good base of understanding for what we're going to be talking about now. You can always catch that online under our webinars section, our archived webinar section online. This webinar will also be recorded and available online in the archived webinar section. So if you do want to check it out later, you can. You can look at the raster webinar first and then check out this one. So other than that, all the phone lines will be muted. And if you do have questions or comments, please feel free to write those down anytime in the chat feature and send those off to me. And we'll get to those questions as we find an appropriate break in time. So thank you so much, everybody, for being here. And let's get started. And my name, again, is Robert Parker. And my email address there is rparker@lizardtech.com. And feel free at the end of this webinar to, if you have further questions, want more information, you can always contact me. That's fine. But let's get started here. First thing, let's talk about what is compression in general. Just a basic understanding. The whole idea is that we want to represent a large amount of data with as few little information as possible. And we can do that by removing redundant information. We can remove excess information. And if you think about really common examples of compression in everyday life, you think about like a restaurant server that's taking your orders. Maybe instead of writing down what each person ordered, she says, okay, well, there's 3 specials and 1 Coke. you know, and then even then in writing it down, she's abbreviating everything, and so there's a form of compression. And no information is lost unless you ordered no onions and you get a plate of a burger with onions on it or something like that. But no information is usually lost there. You can think about a dictionary as well. You can think about abbreviations. You know, if you just say, well, you could replace, if you think about a big paragraph of words, you could replace that with numbers that represent their place in the dictionary, for example, and you might have a nice, smaller, compressed file. And real quickly, you know, like if you think about this Romeo and Juliet here, if we count up the words, we're going to have lots of repetition. So the word her is repeated 9 times. Well, we could replace that with 1 character instead of the 3 that you see there. And that is 8 times. She is 8 times. Phrases are repeated multiple times. So in larger works as well, you get a lot better compression by replacing repeated redundant information with smaller characters. And now let's focus on these 3 terms: lossless, lossy, and visually lossless. So these are terms for compression here. Lossless obviously means there's no loss. It's kind of like a zip file. You know, when you zip up all of your stuff in a zip file, you get it all back again on the other end when you unzip it. Yet the file size for that zip file is much smaller than the combined file sizes of what you've put in there. So you can recover the complete information. All of nothing is lost. Whereas lossy means that some values from your original data are going to be lost forever. There's really no way to recover them. You actually just throw those out, and they get replaced by approximations. And then we have this term when we talk about MrSID, visually lossless. And now that's something that looks like the original, but the changes that you make from being lossy are, you know, so this is lossy we're talking about here, but we call it visually lossless because the changes are unnoticeable. You can look at the original side by side with the compressed version, and if you didn't know which was which, you wouldn't be able to tell. That's what we mean by visually lossless. So let's dive into how you measure compression real quick here. And basically, a compression ratio, like when people say, oh, this was compressed 20:1, 10:1, 30:1, whatever, that ratio of 20:1 is based on the uncompressed size, or the nominal size, divided by the file size. And if we look at that formula for what you get for the uncompressed size, it's always going to be the same. The width, the height, times the number of bands, times the bits, gives us the uncompressed size of that imagery. So for example, a 5,000 pixel wide by 5,000 pixel wide image that has 3 bands, red, green, and blue bands, and each pixel is represented by 8 bits in each band, then we're going to get 600 million bits, and if we do the math, we get 75 megabytes. So we have a 75 megabyte raw pixel size image, and that gives us our uncompressed size. And if the size on disk that it takes up is not 75 megabytes, then that file is compressed. You know, if it's lower than 75 megabytes, we have a compressed file there. So there's a lot of different ways to accomplish a smaller file size and get a compression ratio. And we're going to look at MrSID compression, and we're going to go in depth. And this also applies mostly to JPEG 2000 as well. So just a quick background, MrSID, this whole process, everything was invented at Los Alamos National Laboratories in New Mexico in 1992, or around that time. And it's obviously been improved and worked on since then. But the goal at the time was not just compression. It was also about selective decompression, meaning, let's take a look at an image here, that you can zoom in to a particular area of the image, no matter how large it is, and quickly, selectively just decompress that viewport. If I come in here, we're quickly decompressing that area right there. And if we look at the properties of this image, we can see that it's extremely large. We can see that it's nearly 27 gigabytes worth of data that's packed down into 2 gigabytes file size. So that's pretty impressive from the start. But being able to quickly pan and zoom about that 27 gigabytes worth of data is what MrSID is all about, selective decompression. That's what that term means. So how do we accomplish this? How do we get that compression in addition to this selective decompression? Well, I'll explain what each of these means, but first we're going to go through what's called a wavelet transform, and I'll talk about why we do this and what that brings. The next step in the process is that we go through a color transform, and I will definitely explain each of these as we go. Then we're going to do something called bit planing. We're going to separate everything into bit planes, and don't worry, all of this stuff will make sense. It sounds very technical, but I'll make it make sense, and if you have questions, you can always ask them in the chat. Finally, we do something called binary arithmetic coding. And let's talk about first the wavelet transform. We're going to go through each step of the process, and I'll give you a concrete sample here that'll take us through the algorithm, and hopefully you'll walk away with an understanding of what this all means. So here we have wavelet transform. Now, wavelet transform is basically an algorithm that gives us a special way of organizing and representing our image at multiple resolutions, for one thing, such that we can reconstruct the image from the lower resolution icon. So basically, we have this image representation here, and we can keep reducing this image by half, basically, until we get to this icon level down at the bottom. And that icon level down at the bottom is all we need, plus we've saved some differences as well to reconstruct this full resolution image. So that's what the wavelet transform gives us. It gives us multiple levels so that we can see an overview of the image very quickly, as well as allowing us to save difference bits that help us reconstruct the full resolution image. So let's look at a sample here. I'm going to go dive in to an actual image sample here. We're going to take a 8 pixel wide. We're going to look in one band of the image. So if an image is 3 bands, red, green, and blue, let's just say we're looking at the red band here. And we're looking at the red band, and these are 8 pixels of the red band going from left to right. Now, of course, there would be pixels going in this direction as well, in the vertical direction, but we're just going to look in the horizontal direction here at 8 specific pixels, and we'll run the wavelet transform on those 8 specific pixels. Now, the specific wavelet transform that you're going to see here is called the Haar wavelet, which you can take note of and look up later, but essentially we're taking the average of neighboring pixels, and we're also taking their difference as well. All right, so that's what's happening here. So I'll show you here. With this line of pixels, this 8 pixel line, let's take the neighboring pixels and get their average first. So we get their average. So average here of these neighboring pixels is 42. And then we get their difference, which is 4. All right, and we're going to just keep doing that for each of these neighboring pixels. We get an average 64, an average 65, 37, and their differences. Now, what we're going to store is the differences, which would be all of these values. And we're going to come up with a special name for this, for these 4 values. We're going to store them, and we'll store them right here. And we'll call that a subband. And each one of these levels that we do, we're going to store as a separate subband. And again, the final level here is a subband. And then when we stop doing this process, and in this case, we get down to 1 pixel, so we have to stop. But with a very large image, or with just general imagery in general, we kind of stop at a certain level, maybe level 6, for example. So we'll take that and we'll call that the icon level, and we'll store that as well. So we store these different sub-bands, and those are the differences that make up those sub-bands. Okay. Hopefully you're with me so far. But we have we've stored that information. We've stored the icon, and that all originated from these 8 pixels here. And notice that these pixel values are relatively high, 40, 44, 56, 72, compared to what we actually store. So we're storing lower values here, and that's going to come in handy later, and I'll explain that in a little bit later. So what we're left up with here is that we've stored the icon plus the subbands. The subbands are made up of these differences. So these values here get put right into that subband, right there, just like that. That's how we're going to store them. And just as a visual example, if we go back to this, each one of these are basically the different levels. Here's a level, here's the icon level, here's the other levels, here's the original level. And then here's these differences that we're storing. And in this case, we're only looking at a tiny little section there, just 8 pixels. We're not even looking at the vertical direction. All right, so hopefully this is all making sense. You know, if not, no question is a stupid question. Go ahead, put it in the chat, and we'll get to it. So let's see what's next here. We're going to go. We've made our little storage here. This is what we're storing, these subbands. Now let's see what we do with that information. We're going to take those little subbands, and we're going to run their values through what's called a color transform. Why would we do that? Why would we run it through this process? We do that so that we can separate the intensity and the color. So right now, we have 3 bands, red, green, and blue. Right now, those are all correlated. If you change the red band and make it more intense, then it generally ups the intensity of the overall image. Same thing if you do that with the green and the blue band, and it changes the way the colors appear and all of that. Now, we do a color transform using matrix math, which we won't necessarily get into here. But the color transform we do is similar to a YIQ transform. I won't get into what those values mean necessarily, other than to say that we have a Y band, which indicates the intensity of the image, and these other 2 bands, IQ, just kind of represent the color of the image. And we do this because humans don't recognize even extreme color changes, like 100 times difference in color. But we do recognize even slight variations in intensity. So we're going to get away with modifying the color bands more than we will the intensity bands. Let's just take a look at a quick example here. Here I have on the left an RGB representation of this image. So here's the original image, which is the same in both color representations. But in this one, our 3 bands mean an intensity of red, an intensity of blue, and the intensity of green. Whereas if we look at a different way of representing that, and we don't exactly use YIQ, we use our own patented version, we have 1 band that just represents the overall intensity of the image, and we have 2 bands that represent the color of the image, the color makeup of that image. And we'll be able to essentially, when we do a visually lossless version of this file, we'll be able to get rid of more information in these bands than we would here, thus making our human eyes not really notice the difference. Because we don't notice difference taken out of these bands. We do notice difference, even small differences taken out of this intensity band. So that's why we're doing a color transform. That's why we're doing this. We're just running these pixels that I showed you here, these guys right there. We're going to take each one of those values, run it through a color transform, and they're going to be different values. All right, that's all you need to know really, is that these values that you see here in each subband, we're going to run those numbers through the color transform, and they're going to change. There's going to be 4 different values. And it's not so important what those values are, but for the purposes of this, I even left those values the same. So let's take a look at what we do next. So we're going to have we're going to have different values here, but in this example, I've left them the same. So now what do we do with these subbands? We've run them through a Wavelet Transform. We've created these subbands. We've run them through a color transform to change their values into values that are more efficient for us. And now we're going to convert them into bit planes. And if you're lost in any of this so far, just ask your question, or say how you're lost or whatever in the chat there, and we'll get to it. But let's take a look at what we're doing here. I'm converting these decimal values here, and of course these would be binary from the start, but I'm converting these decimal values here for the purpose of showing you what a bit plane is. I'm going to convert these into binary numbers. So this -10 that you see here is represented in binary by this number. This -14 is represented by this number. This -16 is represented by this number. This 4 is represented by this number. And again, in this subband, we have a 28 represented here, a -22 represented there. These are their binary equivalents. Over here, we've got a -2, and there's the icon right there. So hopefully you can see what I'm doing there, just converting these numbers into their binary equivalents. So it's still the same values, still the same numbers. So now, what we do with bit planing is we're going to take a number like this, for example, and we're going to turn it on its side. So here we have a 0, 0, 0, 0, 0, 1, 5 zeros and a 1, and we see we go down in this direction. 5 zeros and a 1. We see we're going in this direction. And we do that with each of these. We're going to turn this one on its side. So 3 zeros and a 1, you see 3 zeros and a 1 down on its side. And we do that for all the numbers in that subband, and we keep the subband separate. All right, so we've got 4 numbers turned on their side. And those become bit planes because we'll treat them now as blocks of 4 like that. And of course, we'd have much more than 4. We'd have a long string of numbers. But what this does for us is that this makes it so that we have the least significant bits down at the bottom here. These numbers don't change much about the image at all. These are the least significant bits. So for example, if you take a number like, let's say 3,563, the least significant bit here is the 3. If you got rid of that 3, the overall value of this number wouldn't change that drastically. It gets trickier if you move this 5, for example. If you change that to a 4, that's pretty significant. That's 100. That's a value of 100 that you're dropping there. And if you change this 3, that's the most significant. That's if you change that to a 2, you're losing 1,000. A value of 1,000 there. So that's what we mean by most significant and least significant. So we're ordering these planes into the most significant plane down to the least significant plane. This is the key. This is where we can make our visually lossless really mean something. This is how we can do a visually lossless file, meaning this is how we can get rid of data, yet still have it look exactly the same. It's because when we do this bit planing, it enables us to easily just say, get rid of this down here, get rid of this down here. And we can replace these all with zeros, and it doesn't mean as much. It doesn't change the look of the image that much. And I should point out that in combination with the color transform we did, we're going to focus on the intensity band. We're going to focus on the color bands rather than the intensity bands. So remember, in this case, we're just looking at one band, but in reality, we'd have at least 3 bands. And those 3 bands would get converted into intensity and color, and we're going to start with the color bands getting rid of this stuff first. Because, again, our eyes don't notice those changes in color. So that color transform we did really helps us here in this bit planing, meaning that we're going to get rid of the least significant data in the color bands first before we even touch the intensity band. And we're going to start in our highest subblock here, subband here first, and get rid of the stuff there before we move on to these ones here, because getting rid of this stuff would mean a lot more than getting rid of this stuff over here. So hopefully all of that makes sense. This is where the heart of our visually lossless compression is, right here in these bit planes. I should point out that we take these bit planes, and because we're looking at such a small amount of data, we don't really get to see the benefit of subblocks, but we basically divide it up into 64 by 64 chunks of these coefficients of these blocks. So we'd have a 64 by 64 bit, 64 by 64 sub block here, and it's called code blocks in JPEG 2000. that basically make up the image. And why would we do that? Well, I'll show you when we decode the image, but essentially those subblocks mean that we can selectively decode part of the image. And I guess I'll get to that in a little bit. But before we do that, I want to point out one more thing that we do, and just briefly talk about this. And that is we go through binary arithmetic coding, or binary arithmetic coding, as some would say. And I won't get into the details of this unless you really want me to, unless you start asking questions about it. But essentially, we're going to compress those subblocks and subbands into a lossless, using a lossless compression. It's just like zip. So we're gonna take all those zeros and ones, and we're going to represent them with a smaller amount of zeros and ones. You know, if we can represent a whole string of numbers, let's say, 10 numbers represented by just two bits, that's what binary arithmetic coding does for us. It's not so extreme as that unless you have a large amount of data, and usually with image data you do. You can get a nice compression here on those subblocks and subbands. So we're going to run all of these zeros and ones. We're going to turn them into a string of numbers for each subblock is going to become a string of numbers like this. We're going to run it through this little black box here, and it'll be compressed. So then what do we do after that? That's done. It's done. You've made a MrSID file. Of course, there's metadata included with that. But what does that mean? Now you have the SID file. How do you view it? So it's a good question. Let's take a look at an example here. Here, again, is that very large area, very large image. We're going to take this, and let's say we're viewing this. We're kind of looking at the icon level now. Let's say somebody takes this little zoom tool and they draw a box around this area here. So what that means is that the viewer passes on these pixel bounds to us, and we can look and we can say, okay, what subblocks make up that area? So we don't even have to decode the entire image to get there, which means that once they do this, we get a nice fast decode of just that area. We're not decoding the entire image. We're just saying, okay, what subbands and subblocks make up that area? And let's just decode those subbands and subblocks. That's the whole reason we did this wavelet encoding into subbands and subblocks, is so that we could have this selective decode. So now we just need to grab this. We don't need to grab all of the subbands and subblocks. We just need to grab the ones that make up that area. Then we take those, just those, run them back through our color transform, and our specific color transform is of our own creation. It's a patented LizardTech product that is a lossless conversion back to RGB. So we're going from this color transform back to RGB. So we take those subblocks and subbands, convert them back to RGB for display on the monitor. Then we quickly run back through. So let's say we decoded this subband here. All we need are these differences, which we have. We can take this icon. We can go back very quickly back into these directions. So because the difference here was 14, we go 7 in either direction and get those numbers back. And in this case, 10 in either direction, we go 5 in either direction, and we get those numbers back. So it's easy using the numbers that we stored to get back the original values, this line of pixels. Now, if we had thrown out data in this little bit plane area, if we had gotten rid of these little least significant bands, we would have replaced them with zeros, and we would have replaced these with zeros. Not necessarily. Maybe we'd put some ones in there. It's our algorithm just does some error checking and things like that. But if we had done that so that we have a lossy file, we might see some loss when we get these original values back. For example, this 40 might change to 41. Not such a significant difference. Maybe this 72 would be 73 or 71. The differences wouldn't be that significant, but if there was loss, it would be in those pixels. And once we have those pixels, we just push those to screen and we get what you're seeing here. And that's how it works. That's how we can do selective decompression. And if you pan over here, we just get the pixel bounds, and you can see that it just decompresses this area that we're viewing. And makes for a nice compression while still retaining the visual quality of the image. We get a nice, beautiful image that has been compressed, but that doesn't look like it has. And that's all because of what we do. With the Wavelet Transform, the bit planing, color transform, all that stuff combines. So that's it. That's how you make a MrSID file. That's how you decode it. Let's talk about this, give a quick summary here, and then answer questions that you have. So think about your questions, and we'll talk about all of that. So let's see here. We've got our conclusions here. So let's start with the Wavelet Transform. The Wavelet Transform basically helps us organize our image data in a very efficient way for compression. It gives us multiple resolutions of the image so that we can have quick zoom in capability to each different level. It also provides, when we run the pixels through the Wavelet Transform, we come out with lower values that are correlated. So for example, what we'd expect with the neighboring pixel values is that if one is white, then one is going to be a similar shade of white or close to it. And that's typically what we find with imagery, is that pixels are correlated. If one's white, then the other one's probably going to be similar to that white color. The next thing we do is, so we got that Wavelet Transform that gives us that pyramid basically, and gives us our subbands and subblocks. But basically we run all that through the color transform, and the whole purpose of the color transform is to separate the color from the intensity, so that we have an intensity band and we have a couple color bands. And we do that because humans don't really notice even large color changes. I've seen differences of 100 times in color where you really would not notice the difference. And so that's why we do the color transform, so that we can get rid of data in color bands without getting rid of data in the intensity. And then we do the bit planes, because that allows for very fast removal of the least significant bits of the image. And it's simply a mechanism that we use to produce what we call visually lossless compression, where it's lossy, but not lossless, but it's lossy, but not visually so. Okay, and then finally we run that through binary arithmetic coding, which basically is a type of lossless compression that we do on our final bits there after we've done the removal of bit planes. And that takes advantage of all the optimizations we made, because with the Wavelet Transform, those lower correlated values mean that we're going to get a larger string of zeros, which really is very good for the BAC, for the binary arithmetic coding. And yeah, so that's what we do, those 4 steps. Now you know why we do those 4 steps. You've seen a specific example of those 4 steps. We've managed to cram this into a half an hour of discussion here, of presentation here, and it's time for questions. So if you do have questions, please go ahead, write them down in the chat, and we'll get to those questions here. All right, let me take a quick drink of water here, and I'll take a look at the questions that you've had. Remember, this is being recorded, and it will be available online on our archive. And I hope you've had a good learning experience here, that you've taken away something from this, that it hasn't completely been gobbledygook, and that if you do have questions, you can always email me later on if you have to go now. But let's take a look at some questions here. So, all right, let's see. I'll read this one, and then I'll analyze what it means here, and then we'll take a look. So, doesn't using the initial leftmost bit to designate plus or minus take away from the 8-bit data group? hesitate to use byte in this context. Okay, so this person is talking about the way that I have represented my binary number here. So I've got a -10 here, and essentially what I'm doing to represent that negative number in binary. Now, if you're not familiar with binary numbers and things like that, this might be a little bit over the head, but essentially representing this -10 with a binary number, I'm using this first digit as a negative sign. So when you represent negative numbers, you have to do it a certain way. Now, the machine is actually not going to do it this same way that I'm doing it. I'm using it because this is the way we think of numbers. Now, essentially, because we're representing and thinking of our numbers in negative terms, and we only have 8 bits to represent them, he's asking if it takes away the values. Essentially, no, because the values are going to be on a plane. You know, if we think of 0, we're going to go from -127 to +127 instead of from 0 to 255. I think the math works out on there. So all of the numbers that we're going to see here, and especially these are going to be lower values because of the wavelet transform that we did, they're going to end up somewhere in this spectrum here, from +127 to -127. So we're going to be able to represent all the values, no problem. Now, some images are not 8-bit, some are 16-bit, but we do the same kind of thing, just with higher positive and lower values. Hopefully that makes sense. This is the way we think of the numbers. In actuality, the machine stores them somewhat differently. Not using this bit, it kind of does an inverse storage of the numbers there. Hopefully that answers your question. If not, we can go into an email or talk about it later. Appreciate all the comments that folks are writing in, and really appreciate everybody being here. I know with this thing, with this kind of discussion, things can get confusing, but hopefully I've made it presentable for you here. And again, I'll put my email address up on the screen. And you can always contact me with questions or comments. We can always discuss this more if you want to discuss it. But there it is, rparker@lizardtech.com. Totally appreciate you guys being here. And again, this will be on our website at lizardtech.com in the archive section of our webinars. Thanks everybody for coming. That's all the time we have. And have a really great week and great weekend. And may this knowledge benefit you in many ways. All right, thanks again, everybody. Take care. Bye for now.